All right, so today we're going to talk about volumes by slicing. We'll talk about volumes of revolution, I believe starting tomorrow. But so far we've done area. We haven't done anything really three-dimensional yet. But here's the idea, is that the volume of a solid of known integrable cross-sectional area, A of x, from x equals a to x equals b, is simply the integral of a from a to b. So that is, the volume is the integral from a to b of the area of a particular slice times dx, which is the thickness of that slice. So if you think about this in terms of something simple, let's say you have a square, and you know the area of a cross section, and then you knew how thick your little slice was. You could multiply the area times the thickness, and that would give you the volume of that little slice. Then the integral simply adds all those together. Okay? There are all kinds of cross sections that you can have. Here are some of the more common ones. Most of these you know the formulas for and have for some time. Area of a square is side squared. Area of a rectangle is base times height. Area of a triangle is half base times height. One that you may have forgotten because you don't use it, you used it in honors geometry but probably haven't used it since, is the area of an equilateral triangle. That's side squared times the square root of 3 over 4. You may or may not remember that one. The area of a circle, pi times the radius squared. Hopefully you know that one. The area of a semicircle, I've given you 1/2 pi r squared, which is true, but more often on this, you're going to not have the radius, you're going to have the diameter. So for that one, I keep punching the wrong colors. So area is equal to 1/2 pi times the diameter over 2 squared. Or if you prefer, 1/8 pi times the diameter squared. That's a handy formula to know. Most of the time on these, when you have a semicircle, you don't have the radius, you have the diameter. And then the last one, an annulus. This is something you probably haven't thought of before. We did some things like this in honors geometry. This is an annulus. The annulus is all this stuff out here. More like a washer, because it's a flat. But yes, God bless you. And we've got the radius of the inner circle, and capital R is the radius of the outer circle. So basically what you're doing is you're finding the area of the whole circle minus the area of the part that's not part of the circle, part of the annulus, the part that you've cut out, the hole in the washer, if you will. Okay, let's look at some example problems of these and how this is going to work out. And they frequently start like this. The base of a solid is the region R enclosed by the graphs of y equals 2 sine of x and y equals x in the first quadrant. What I want you to think of when you think of this is, have you ever looked at the floor plans for a building? Or for like an apartment or something like that where it's, this is how it's laid out? That's what this is. It is the floor plan. Okay? Unlike a regular building though, this isn't going to be a building where the walls go straight up. This is going to be a building where the walls curve or do weird things like that. Okay? But this first part, that's just the bottom. Then here it says each cross section cut perpendicular to the x-axis is a square. Okay? Do you need to be able to visualize this in 3 dimensions? No. I have some colleagues that I've talked to about this at length and I couldn't convince them, but I have some colleagues that teach this that spend 3 or 4 days building models of these. I'm like, that is a waste of time because you don't need to be able to visualize it in 3 dimensions. You need to be able to visualize the floor plan, the base, and then from there you just need to know, well, what is the cross section and what part of the cross section is on the floor, is in the base. That's all you really need to know. So find the volume of the solid. So first step, I'm going to sketch this. So again, think of it like it's a floor plan. It said it's in the first quadrant. Y equals 2 sine of x. So that looks something like this. Right? Kind of looks parabola-ish. And then y equals x. A line that looks something like that. So the region between here and here is our base. This is clearly at 0, 0. Let's see if we can do this one by hand. There's going to be some that we absolutely cannot. Yeah, actually this is one that we cannot. Y equals 2 sine x and y equals x. If you try to solve that, it's like, well, what the heck are you going to do? Right? Because you've got a trig function over here and a polynomial function, although a pretty low-level polynomial function, but a polynomial function over here. So we're going to have to use our calculators to find where these two intersect. So we've got 2 sine of x and y equals x. And you know, my zoomed in from the last one was probably about the right part. Okay, so we can see the intersection. It's somewhere close to x equals 2, but it looks to me like it's a little bit less than that. So let's find the point of intersection. First curve, second curve, it's somewhere close to 2. 1.895. Again, I'm off in the thousandths place this time. So I'm off by, actually I'm closer to, no, I'm only off, if I said it was 2 by a tenth, a little over that. So this point has coordinates, 1.895, yada, yada, yada. And again, don't round that. Okay? Now, so we've got the points of intersection, so we know everything we need to know about the base. And it says each cross-section cut perpendicular to the x-axis is a square. So again, this is the floor. The building is actually coming up at you out of your page. Again, it's not important that you can visualize what this whole building looks like, but a cross-section perpendicular to the x-axis would be like this, right? That's only part of the cross-section. That's the part of the cross-section that goes all the way down to the base.
So is the base all of the parabolic region in the first quadrant, or just that that's above the x-axis? Or above the x?
It's just this part.
Okay.
So the part that we are addressing is this. That's our floor plan. Okay? So the question becomes, well, it says the area is that of a square. What's the formula for the area of a square? Sine squared is a better one for this because the base and the height are the same. What part of the square is this piece right here.
The width?
It's a side of the square,
Okay.
right? So the square is actually coming up at you. So this is a side of the square. So this curve up here, this point, is just some random x value, right? This is x, comma, 2 sine of x. And the corresponding point below it is x, comma, x, because the y value is equal to x. And that's the length of the side. So the area in terms of x is going to be, well, how do I find the length of this? It's just 2 sine x minus x. Wherever you are, s is going to be 2 sine of x minus x. So the area will be 2 sine of x minus x quantity squared. So then the volume will be the integral from where they first met, which was at 0, to 1.895, yada, yada, yada. And your integrand will be 2 sine of x minus x quantity squared, all dx. Again, you can do all that on your calculator. So, math 9. Oh, let's get out of that. Try that again. Math 9. The integral from 0 to, since I didn't move my graph, if I'm on wherever x was, it should still have that. If you want to save it as a or b or whatever each time, you're welcome to. And if you have more than one, you have to. And this is going to be parentheses y1 minus y2 squared with respect to x. So it's 0.456. If this is a calculator active problem, there's absolutely no need to expand this expression. Okay? Any questions about that one? Let's do another example. Find the volume of a solid whose base is the region in the xy plane bounded by the graphs of y equals x squared and y equals 8 minus x squared, and whose cross-sections, perpendicular to the x-axis, are semicircles with diameter in the xy plane. Okay. So let's start by sketching a graph. We've got y equals x squared and y equals 8 minus x squared. All right. So both parabolas, y equals x squared, an upward facing parabola, 8 minus x squared, a downward facing parabola. They're really supposed to be the same width, but it gets you what you want. We do need to know where these two intersect. So if I have x squared is equal to 8 minus x squared, I've got 2x squared equals 8. So x squared equals 4. So x equals, or, yeah, always think about both the positive and the negative square root. So this point and this point, this is going to be 2, 4, and this is going to be negative 2, 4. And it says if I take a cross-section perpendicular to the x-axis, so I'm going to just pick a random spot and go, this is my little slice. I like to go over it a couple of times because I want to think about this has some thickness, dx. This curve again, x coordinate is x. The y coordinate is 8 minus x squared. And this point will have coordinates x, x squared. What part of the semicircle is this? It tells you in the problem. It's the diameter of the semicircle. So our area formula is pi over 8 d squared for a semicircle. So the area in terms of x is going to be pi over 8 times, well, what is the diameter in terms of x? Exactly, 8 minus x squared, which is pi over 8 times 8 minus 2x squared. So the volume will simply be the integral from negative 2 to 2 of the area, pi over 8 times 8 minus 2x squared dx. So that's pi over 8 times 8x minus 2/3 x cubed from negative 2 to 2. So it's pi over 8 times 16 minus 16/3 minus negative 16 plus 16/3. So that's pi over 8 times 32 minus 32/3, which is 4 pi minus 4 pi over 3. In all likelihood, if this is a multiple choice question, they're going to get a common denominator by multiplying this by 3 over 3, so that would be 12 pi minus 4 pi is 8 pi over 3. That's likely to be the answer that they give. Okay, any questions about that one? All right, one more then. Let S be the region in the first quadrant bounded by the graphs of y equals x squared, y equals 4, and the y-axis. S is the base of a solid in which every cross-section perpendicular to the y-axis is a rectangle whose height is 6 times its base. Find the volume of the solid. Okay. Well, we'll start again by graphing this. We only want the part in the first quadrant, so I only need to draw first quadrant stuff. I've got y equals x squared, so basic parabola. And y equals 4. So a line like that. And the y-axis. Okay. And actually, they didn't have to tell you the y-axis because they told you it was the part in the first quadrant.
It's a quarter circle.
Not really. It's closer to a quarter ellipse than anything else. But even then, if you connected these, they wouldn't connect smoothly. This time, though, we want our cross sections to be perpendicular to the y-axis. So instead of wanting things to be in terms of x, we want things to be in terms of y. So let's find where these two intersect. The coordinates of this are going to be, that's pretty easy, 2, 4. This point is 0, 4. This point is 0, 0. This point, well, the x-coordinate is going to be 0, right? And the y-coordinate is going to be some random y value. And if y equals x squared, then what does x equal? Or, yes, every time you take the square root, I want you to think of positive and negative square roots. Which one do we have in this first quadrant? The positive root. So this is going to be, the x-coordinate is the square root of y, and the y-coordinate is whatever the y-coordinate is. So what part of the rectangle is this? It's the base. So the area of a rectangle is?
Or base times height.
Base times height. But for this particular one, it says the height is 6 times the base.
So base times 6b.
So b times 6b, which is more simply stated 6b squared. So our area in terms of y is going to be 6 times, what is this distance?
B. Oh.
But in terms of y?
Y minus, no. Just negative square root of y. It's just y.
No. And no.
Is it 0 minus the square?
Which one is bigger, the square root of y or 0?
Square root of y.
So it's
negative the square root of y, yeah. No negative. Square root of y.
It's the square root of y minus 0, which is just the square root of y. Remember, when you're slicing perpendicular to the y-axis, it's always right minus left because you want the larger value. So this is just going to be the square root of y squared. Well, what could be nicer than that? That's just 6y. So my volume will be the integral of the area. And again, this is with respect to y. So what should my limits of integration be?
0 and 4.
0 and 4, exactly right. Because we're going to start slicing down here where y is 0, and we'll keep slicing until we get up here where y is 4. So that's going to be what? 3y squared from 0 to 4 is 48. Okay? So, identify the area in general. Find the area in terms of either x or y, depending on which one you're slicing perpendicular to. Integrate. Okay?